Artemis 2 looks like a return to the moon, but it is really a test of something bigger. Apollo 11 proved humans could reach another world once. Artemis 2 has to prove we can go beyond Earth, in a way that is safe, repeatable, and real. That is what makes this mission so important. It is not about repeating the past, it is about proving the future can work. Apollo 11 was a lunar landing mission. That was the point of the mission, the pressure of the mission, and the reason the world watched. It had to launch, head to the moon, enter lunar orbit, send 2 astronauts down to the surface, bring them back up, dock again and return to Earth. Every major step pointed toward one moment on the surface. Artemis 2 does not do that. Artemis 2 is a crewed lunar flyby and a systems validation mission. It carries astronauts around the moon and back, but its main job is to test the hardware, the operations, and the human side of the mission under real deep space conditions. That means Orion, the space launch system, navigation, life support, manual control, communications, and recovery all have to prove themselves with people inside the vehicle, not just with simulations and uncrewed flights. That sounds less dramatic if you only care about footprints, but if you care about whether later crews can survive, then Artemis 2 becomes very serious very fast. NASA is not using this mission to ask, can we repeat Apollo? NASA is asking, can we build a transport system that can support many lunar missions instead of one famous landing? That is why judging Artemis 2 by asking whether it lands is the wrong way to look at it. It is like judging a bridge test by asking why no one is living on the bridge yet. First you prove the structure, then you trust people with it. So look at the mission logic and the difference becomes obvious. Apollo 11 moved in a straight line toward a landing attempt. Launch, translunar injection, lunar orbit insertion, separate the lander, descend, walk, launch back up, rendezvous, come home. It was tightly focused and brutally compressed. Artemis 2 follows a different logic. 4 astronauts launch together. They spend about 10 days checking whether the whole stack works the way it should in flight. They enter Earth orbit first, then move into a very high Earth orbit for checkout work. They test manual piloting. They evaluate life support. They check how the spacecraft behaves with a full crew. Then they fly a free return path around the moon and come back to splash down in the Pacific. Apollo 11 said, "Can we touch the surface?" Artemis 2 says, "Can this architecture support a campaign?" That word matters. Architecture. Apollo 11 was a mission. Artemis 2 is part of a larger system. Apollo 11 had to prove one nation could get there first. Artemis 2 has to prove that the modern system can support later missions that will involve docking, operations near the moon, surface landings, and the long chain of logistics needed for a sustained presence. So even though Artemis 2 sounds more cautious, it is actually carrying a broader burden. It is not trying to create one iconic moment. It is trying to reduce the chance that future crews are sent into deep space on a machine that still has major unknowns. Then there is the flight path, and this is where people usually realize the mission is not just a scaled-down Apollo. Apollo 11 entered lunar orbit and then split the mission into 2 spacecraft solving 2 different tasks at the same time. One spacecraft stayed in orbit with Michael Collins. The other carried Neil Armstrong and Buzz Aldrin down to the moon. Artemis 2 does not do that. It does not insert into lunar orbit for landing work. It follows a figure-8 style path that reaches more than 370,000 kilometers from Earth, more than 230,000 miles, and uses a free return trajectory. That means the geometry of the Earth-Moon system helps pull Orion back home. On paper, that sounds less intense than a landing. In engineering terms, it is exactly the kind of mission that reveals whether your deep space transport system is actually ready, and that is the uncomfortable part. Artemis 2 is not smaller in any simple engineering sense. It is narrower in goal, but wider in what it has to validate. Apollo 11 had to survive the most famous landing attempt in history. Artemis 2 has to prove that NASA can stop treating deep space like a one-time gamble. It has to show that human beings can live and work in Orion beyond low Earth orbit, that the spacecraft can be flown and monitored the way it was designed to be flown and monitored, and that the return from deep space can be handled as a repeatable operation, not just as a dramatic ending. You can feel the program change right there. Apollo 11 came out of a race. It was shaped by a deadline, by Cold War pressure, and by the need to do something first. Artemis 2 comes out of a very different mindset. The pressure is not only to succeed once, the pressure is to build something that can be used again and again without pretending every mission can survive on courage and luck. That makes Artemis 2 less clean as a story, but more important as a test. It is not trying to win a symbolic victory, it is trying to expose weaknesses before those weaknesses can kill someone on a landing mission. That is why the mission feels different even before you get to the moon. Apollo 11 was aimed at the surface from the start. Artemis 2 is aimed at trust. Can the crew trust the spacecraft? Can mission control trust the data? Can NASA trust the procedures, the life support systems, the navigation, the handling and the recovery chain enough to commit the next crew to a real landing attempt? Those are not glamorous questions, but they are the questions that decide whether a space program matures or collapses. So the first shock is this. Artemis 2 is not trying to be Apollo 11. It is not a failed version of Apollo 11, and it is not a safer copy of Apollo 11. It is solving a different problem because NASA is trying to build a different future. Apollo 11 changed history with the first landing. Artemis 2 is trying to prove that history after the landing can actually function. If Apollo 11 was the first footprint, Artemis 2 is the first serious audit of whether human deep space flight can become a real operating system instead of a rare event. And once you see that, the stakes do not go down. They go up. Because if Artemis 2 fails, it does not just delay one mission, it raises doubts about the whole architecture behind the missions that come next. Then why does the crew already make this feel like a different program before the rocket even moves? Because the people on board tell you what kind of mission this really is. Apollo 11 flew 3 astronauts, Neil Armstrong, Buzz Aldrin and Michael Collins. Artemis 2 flies 4, Reed Wiseman, Victor Glover, Christina Koch and Jeremy Hansen. That is not just one more seat. It changes how work gets divided, how the spacecraft is used and what kind of mission NASA thinks it is running. Apollo 11 looked like a mission built around one historic act. Artemis 2 looks like a mission built around operating a deep space system as a team. That difference starts with something very basic: volume and workload. A crew of 3 and a crew of 4 do not live the same way, do not move the same way, and do not manage time the same way inside a spacecraft. Apollo 11 was built around a smaller crew because the mission architecture demanded a very specific split. 2 astronauts would go down to the moon. 1 would stay alone in lunar orbit. The crew size matched that plan. Artemis 2 is carrying 4 because the mission is not a landing attempt. It is a full-up crewed test of a transport system. More people means more tasks can be handled in parallel. It also means NASA is testing whether Orion can support a larger team under real deep space conditions. So when you see 4 people instead of 3, that is not a cosmetic update. It is a clue that the mission has moved away from a narrow landing operation and toward a broader operational test, and the role map makes that even clearer. Apollo 11 had a command module pilot for a very specific reason. Michael Collins had to stay in Columbia, while Armstrong and Aldrin went down in Eagle. That was the structure of the mission. 1 astronaut remained in lunar orbit, managing the command spacecraft, while the other 2 handled descent, landing, surface work and ascent. The job titles reflected the architecture exactly. Artemis 2 does not carry a lunar lander. There is no separate vehicle dropping to the surface. There is no split between orbiter crew and lander crew because there is no landing phase at all, so the roles are different. Artemis 2 uses a commander, a pilot and 2 mission specialists because the work is different. The mission is about spacecraft operations, flight test objectives, systems demonstrations, science support, and building confidence in procedures that later missions will need. That sounds less dramatic than lander crew, but it is actually very revealing. Apollo 11 divided the crew around a landing. Artemis 2 divides the crew around operating and evaluating a deep space vehicle. So the names of the jobs already tell you the story. Apollo 11 had roles shaped by one immediate goal: get 2 people to the surface and back. Artemis 2 has roles shaped by a mission that must watch, check, test, record, and validate constantly. That changes the culture inside the cockpit. It is less about one central heroic move and more about managing a machine that future crews will depend on. In Apollo 11, the role structure pointed toward one irreversible event. In Artemis 2, the role structure points toward repeatable operations. That is a major shift, and it happens before you even touch the moon. Then there is the part people often treat as symbolism first and operation second. That is backward. NASA says Artemis 2 includes the first woman, the first person of colour, and the first Canadian on a lunar mission. Those are historic facts, and they matter. But they're not just there to make the mission look modern. They also show that the program itself has changed. Apollo 11 came out of Cold War competition. It was an American mission built to prove national capability in a race against another superpower. Artemis 2 comes out of a different model. This program is built around long-term partnerships. Jeremy Hansen is on this crew because international partnership is now built into the architecture itself. It is not an afterthought. It is not a diplomatic gesture after the mission is over. It is part of how the mission exists in the first place. That matters more than it first seems. In Apollo, the world watched, but the system was national. In Artemis, the world is not only watching. Parts of the mission are shared structurally. The crew itself reflects that. So when you see this lineup, you're not just seeing a more diverse crew in a cultural sense. You're seeing a program that expects international participation to be normal, necessary, and permanent. That is a deep change in how lunar exploration is organised. Apollo 11 showed what one nation could do under maximum pressure. Artemis 2 is starting to show what a coalition-era exploration program looks like when it puts humans on board. And that leads to a harder question. What kind of crew culture do these missions need? Apollo 11's crew had to solve a brutal first-time problem. They were attempting the first lunar landing in history with very little real precedent. Armstrong's manual control during descent became legendary because the mission compressed so much risk into one irreversible attempt. If that landing failed, the whole mission changed instantly. Apollo 11's crew culture had to be calm under pressure, technically precise, and ready to make decisions inside a situation that had never existed before. It was a mission culture built around one narrow peak of danger. Artemis 2 is dangerous too, but in a different way. Its crew is not training for one all-or-nothing landing sequence. Its crew is training for manual proximity operations, deep space system checks, geology observations, health protocols, communications procedures, and contingency responses. That is a different burden. The goal is not to win a single historic moment. The goal is to generate confidence in the whole operational chain so later crews can trust it. That means the crew has to function not just as astronauts in the old sense, but as operators, observers, evaluators, and data sources all at once. Apollo 11 needed a crew that could execute the impossible once. Artemis 2 needs a crew that can help make future missions less uncertain. That is why the comparison should not stop at counting seats or naming milestones. The crew composition is part of the mission logic. Apollo 11 was the sharp end of a national race. Artemis 2 is the first human crew of a transport system meant to support later landings, later science, later infrastructure, and eventually Mars. These 4 people are not only going around the moon, they're showing you what kind of program this is now. A larger crew, different roles, partner representation built into the structure, training built around system confidence instead of one landing attempt. Even before you look at the rocket or the spacecraft, the crew already tells you the architecture changed. And once the people on board reveal that the mission has changed this much, the next question gets even bigger. If the crew is different because the system is different, then how different is the machine that lifts them off Earth? Then the next assumption breaks too. You hear moon rocket, and your brain immediately jumps to one simple question. Is SLS just a modern Saturn V? No, that is too simple, and it hides the real difference. These two rockets are not just bigger versus smaller or stronger versus weaker. They are built around different ideas of what a moon program is supposed to be. Start with the numbers, because this is where people usually think they already know the answer. NASA's SLS Block 1 stands about 98.1 meters tall or 322 feet. Fully fueled, it weighs about 2.61 million kilograms or 5.75 million pounds. During launch and ascent, it produces about 39.1 meganewtons of thrust, or 8.8 million pounds force. NASA says that's about 15% more thrust than Saturn V had at liftoff, but then the comparison gets more interesting. Apollo 11's Saturn V first stage started at around 34.0 meganewtons, or 7.65 million pounds force, and as it burned propellant and got lighter, its thrust rose above 40.4 meganewtons, or 9.09 million pounds force, before center engine cut off. So even right there, the clean story falls apart. One vehicle has more thrust right at liftoff, the other grows stronger through the burn and peaks higher later. That tells you something important immediately. These rockets are not just versions of the same machine separated by time, they are powerful in different parts of flight and designed around different ascent logic. So what actually changed? The propellant story tells you more than most people realise. Saturn V used RP-1 kerosene and liquid oxygen in the first stage, then liquid hydrogen and liquid oxygen in the upper stages. That first stage was built for raw push. Kerosene and oxygen gave Apollo enormous initial force and helped drive the vehicle off the pad in a program that was built to get to the moon fast. SLS does it differently. Its core stage uses 4 hydrogen-oxygen RS-25 engines, and it gets extra liftoff force from 2 giant solid rocket boosters on the sides. That is a very different combination. You are looking at a rocket built partly from shuttle-era heritage, with updated avionics, modernized systems, and a design intended to support a sequence of missions. Saturn V came out of a crash program aimed at one national objective under a hard deadline. SLS comes out of a slower, more constrained environment where reusing proven technology, meeting modern safety expectations, and surviving budget pressure all matter. That is why the hardware looks different even when the mission destination sounds similar. Saturn V was built in an era that accepted a level of industrial risk and urgency that is almost hard to imagine now. SLS is built in an era where every major design choice lives inside decades of lessons from Apollo, shuttle, uncrewed programs, cost overruns, and modern oversight. So when people say SLS is just old power reheated, they are missing the point. Some of the lineage is old, the philosophy is not. Then you get to the engines, and this is where the character of each rocket becomes obvious. The Saturn V first stage used 5 F1 engines, and they were enormous. Each one was more than 5.5 meters tall, over 18 feet, and each one burned almost 3 tons of propellant every second. That is the kind of number that sounds abstract until you slow down and think about it. One engine burning roughly that much mass every second means the first stage as a whole was turning fuel into force at a scale that still feels almost unreal. It was direct, brutal, and built to move a huge moon vehicle with no hesitation. SLS uses a different kind of power. Its 4 RS-25 engines are smaller and far more refined, each producing about 512,000 pounds force of thrust. Together, those 4 contribute about 2 million pounds force. The rest of the climb force comes from the 2 solid rocket boosters, which deliver the massive extra push needed at liftoff. So instead of Saturn V's 5 giant kerosene engines dominating the story, SLS spreads the job across high-performance liquid engines and very powerful solids. That changes how the vehicle behaves, how it is controlled, and how people think about it. Saturn V feels like a rocket designed to overwhelm the problem. SLS feels like a rocket designed by combining precision liquid propulsion with extremely strong booster assistance. Same broad mission class, very different method. And the difference is not only in force, it is also in brains. Apollo 11's Saturn V used an instrument unit that made guidance calculations about once each second. It worked through inertial guidance and launch vehicle computers that, by modern standards, sound ancient. But that does not mean it was crude. It means it was doing extraordinary work with much more limited computation. The achievement was enormous for its time. SLS lives in a completely different computing world. Its avionics and flight software, developed at Marshall and elsewhere, sit on top of decades of improvement in control systems, sensors, software engineering, and fault handling. It can process, monitor, and react in ways Apollo-era systems simply could not. But even there, the comparison is not old bad, new good. That is lazy too. The real point is that both rockets sit inside systems that still leave room for human authority when automation is not enough. Apollo never treated astronauts as cargo. Artemis does not either. The machines got smarter, but the deep truth stayed the same. When human beings are on top of millions of pounds of propellant leaving Earth, authority and trust still matter at every level. That continuity matters because it shows the philosophy did not become fully automated just because the computers improved. So which rocket is better? That is the wrong question. Saturn V was built to solve one historic problem under maximum urgency: put Americans on the moon before the decade ran out. It was a giant launcher made for a deadline. SLS is built to restart human deep space operations under modern safety rules, modern software, and modern manufacturing realities. It is supposed to support a campaign, not just a single victory. Saturn V belonged to a race, SLS belongs to a program trying to prove it can endure, and that should change how you see the comparison. Saturn V was not simply the glorious old version and SLS the careful new version. Saturn V was a machine optimized for a national sprint. SLS is a machine optimized for a slower, harder task, building the launch side of a repeatable deep space system in a world that no longer accepts Apollo-style risk, Apollo-style urgency, or Apollo-style freedom of design. Same destination family, completely different philosophy. And once the rocket itself stops looking like a simple remake, the next question becomes even sharper. If the launcher is different because the whole program is different, then what about the spacecraft sitting on top of it? So if the rocket is different, then what exactly is sitting on top of it? This is where a lot of people still think in Apollo terms and miss what changed. Apollo 11 was not one simple spacecraft. It was really three major pieces working together in one mission. You had the command module, VE, which was the crew's control center and living space. You had the service module, which carried propulsion and support systems, and you had the lunar module, Eagle, which existed for one reason: take 2 astronauts down to the moon and bring them back up to lunar orbit. That meant Apollo 11 had to dock, undock, descend, land, launch from the surface, rendezvous, and dock again just to complete its basic plan. Artemis 2 does not do that. Artemis 2 flies Orion with its European service module and no lunar lander at all. That is not a missing piece. That is the point of the mission. And that changes the whole meaning of the spacecraft. Apollo's system had a built-in split personality. One part had to keep astronauts alive in lunar orbit. Another part had to go down to the surface and back. Those were different jobs with different engines, different structures, different risks, and different failure paths. That made Apollo incredibly capable, but it also made it extremely complicated. Artemis 2 removes that entire landing layer because this mission is not trying to complete the full moon landing chain. It is testing the crew transport system itself. So instead of asking one spacecraft stack to do everything at once, Artemis 2 asks Orion to prove that it can safely carry astronauts through deep space and bring them home. That sounds simpler, but it also means the pressure shifts. The spacecraft is no longer just a step on the way to the real mission. For Artemis 2, the spacecraft is the real mission. You can even feel that change in the living space. Orion's habitable volume is about 9.34 cubic meters, or 330 cubic feet. NASA says that is roughly like 2 minivans. It is also nearly 60% more space than the Apollo command module, which had about 5.95 cubic meters or 210 cubic feet. That does not make Orion spacious. 4 people in that volume for a deep space mission is still cramped, but it does change the kind of mission you can run. Apollo 11 treated tight living conditions as something the crew simply had to endure in order to reach a landing attempt. Comfort was not the point. The landing was the point. Artemis 2 still accepts confinement, but now the volume itself is part of what is being tested. Can 4 humans live and work inside Orion for days beyond low Earth orbit? Can they move, sleep, operate systems, manage procedures, and stay effective in that environment? That is not a side detail. That is one of the reasons the mission exists. So the extra space is not about luxury, it is about function. Apollo's command module was small because the mission design pushed almost all its complexity into the landing architecture. Orion has to be more of a working transport vehicle. It has to support a larger crew and a longer list of operational checks. That changes the feel of the mission. Apollo's cabin was the cramped core of a landing stack. Orion is the center of a deep space transport test. It still gets tight, it still demands discipline, but now cabin volume matters as an operational factor, not just as a sacrifice everyone accepts to make history. Then look at the service module, because this is one of the clearest signs that the whole program changed. Orion's European service module, built by ESA, provides electricity, water, oxygen, nitrogen, thermal control, and propulsion. It is about 4 meters long, and once the fairing is gone, its solar arrays open out to span 19 meters, about 62 feet. That is not a small detail. Apollo's service module was American-built and designed inside a national moon race program. Orion's service module is literally international hardware carrying a human lunar mission. That tells you the exploration model is different at the structural level. This is not one nation building every critical piece alone and then inviting the world to watch. This is a partner-built system where international contributions are part of the spacecraft itself. That changes the meaning of the vehicle in a way people sometimes underestimate. In Apollo, international prestige came after the mission. In Artemis, international integration is already inside the machine before launch. The service module is not a symbolic add-on. It handles core survival and propulsion functions. Without it, Orion is not doing this mission. So when people say Artemis is just another moon program, that misses something basic. Apollo's hardware reflected a national race. Orion already reflects a coalition-based exploration model. Then there is the biggest architectural difference of all. Apollo 11 needed a separate lunar brain. Because it carried Eagle, Apollo had to divide risk between 2 pressurized spacecraft with different propulsion systems and different jobs. The command service module had to keep functioning in lunar orbit. The lunar module had to separate, descend, land, launch back up, and rejoin the main spacecraft. That meant the mission depended on 2 different vehicles solving 2 different problems in sequence. If either one failed in the wrong way, the consequences were immediate. That is why Apollo's architecture was so powerful and so unforgiving at the same time. Artemis 2 removes that entire category of risk because it is not landing. No separate lander, no surface descent engine, no ascent from the moon, no lunar rendezvous after a landing. At first, that can sound like a simpler and smaller mission, but that is only true if you think the landing is the only thing that matters. The meaning of Artemis 2 shifts upward. The mission is not trying to validate a full end-to-end landing stack. It is trying to validate the deep space transport layer that later missions will depend on. In plain terms, NASA is isolating one major part of the larger system and testing it with a crew before adding even more complexity on top. That is why the architecture matters so much. Apollo's architecture was optimized to solve one hard problem on a deadline, put humans on the moon fast enough to meet the national goal. Every design choice served that pressure. Orion is optimized for a different purpose. It is meant to be a reusable pathfinder for repeated missions in lunar vicinity, not a one-shot vehicle built only for one historic moment. Apollo 11 carried a lander because the mission was the landing. Artemis 2 carries no lander because the mission is the transport system itself. That is the cleanest way to understand the difference. And once you see it like that, Orion stops looking like a weaker version of Apollo's spacecraft stack. It is a different kind of machine for a different stage of the program. Apollo's system was designed to reach the surface as fast as possible. Orion is being used to prove that crews can travel out, operate in deep space, and come back in a way future missions can build on. Apollo divided itself because the mission demanded it. Artemis 2 stays unified because the mission is focused on the transport vehicle as its own test article. Different architecture, different job, different standard for success. And that raises the next problem immediately. If the spacecraft itself is now the mission, then even the trip away from Earth cannot work the way Apollo did. So what happens when the route to the moon changes too? Then the route itself changes, and that is where the mission stops looking like Apollo in any normal sense. Apollo 11 got into Earth orbit and did not stay there long. 2 hours, 44 minutes after launch, the S-4B stage reignited for a second burn that lasted 5 minutes, 48 seconds, and sent the crew toward the moon. Artemis 2 does not leave Earth that way. NASA's current Artemis 2 mission profile has Orion and the upper stage orbit Earth twice first, then move into a high Earth orbit, and then spend roughly 23 hours there while the crew checks systems and stays relatively close to home before committing to the trip outward. That is not a minor timing change, it is a different philosophy. Apollo moved toward the landing plan as soon as it could. Artemis 2 pauses and checks the machine before it lets distance make every mistake harder to fix. And the orbit numbers make that difference very clear. Apollo 11 launched into an initial Earth orbit of about 114 by 116 miles, about 183 by 187 kilometers. That was a parking orbit. It was a waiting room before the moon mission really began. Artemis 2 goes much farther before it even counts as fully leaving Earth. NASA says Orion will be refined into a high Earth orbit of about 44,525 by 115 statute miles, which is about 71,656 by 185 kilometers. That is an extremely stretched orbit. One end stays relatively close to Earth. The other reaches so far out that Orion is already operating in a regime that feels much more like departure than ordinary Earth orbit. Apollo used Earth orbit as a short setup phase. Artemis 2 uses high Earth orbit as part of the test itself. So if Apollo had a docking problem to solve, what replaces it on Artemis 2? Apollo 11 had to do something immediately critical after translunar injection. The command service module separated from the S-4B, turned around, docked with the lunar module, and then pulled it out before leaving the stage behind. That maneuver was not optional. It was built into the mission from the start. Artemis 2 removes that entire docking requirement because there is no lunar lander aboard. But NASA does not waste the opportunity. Instead, Artemis 2 uses the upper stage as a target for a manual proximity operations demonstration. The crew will switch Orion into manual mode and fly around that target to collect performance data and practice handling that future missions will need for rendezvous and docking near the moon. Apollo docked because the mission demanded it right away. Artemis 2 flies manually because the mission is preparing for what later missions will demand. That tells you something important about how NASA now thinks about skill. Apollo 11 treated early Earth orbit operations mainly as the path to commitment. Once the systems looked good, the mission pushed outward. Artemis 2 treats that same general phase as a controlled training and validation environment. Manual flying is not just there in case something goes wrong, it is a planned test point. NASA wants real crew handling data in space, not just simulator confidence on the ground. That is a major change in mindset. Apollo had to trust that the crew could execute when the moment arrived. Artemis 2 wants to measure crew and vehicle performance before the higher risk missions begin. Communications also change earlier than most people expect. Artemis 2 will briefly move beyond the range of GPS satellites and NASA's tracking and data relay satellites while it is still in Earth orbit. NASA is doing that on purpose so the mission can check deep space network communication and navigation capability before Orion heads farther out. Apollo 11 worked through the manned spaceflight network, a worldwide chain of stations, ships and aircraft that handed coverage across the planet and kept the mission in contact as continuously as possible. So the contrast is sharp. Apollo used the departure phase mainly as transit supported by a global network. Artemis uses the departure phase as a systems lab, where even the handoff from near-Earth support to deep space support gets tested before the real outbound leg is underway. And this is the point where the break between the two eras becomes impossible to ignore. Apollo 11 left Earth like a mission already committed to a landing sequence. It checked what it needed to check, and then it went. Artemis 2 leaves Earth like a mission that knows deep space operations have to be inspected, rehearsed and measured before the landing campaign can safely begin. That does make the mission less simple to describe. It also makes it much more useful as a foundation. Apollo sprinted because it was built for a single historic objective. Artemis verifies because it is trying to support repeated missions after this one. And once the trip away from Earth becomes a test program instead of just a transit, the next question gets even sharper. When Orion finally reaches the moon, is the moon still the target, or has it become something else entirely? Then the moon itself changes roles, and this is where the difference becomes impossible to miss. Apollo 11 went to the moon to land. Artemis 2 goes to the moon to learn how to operate near it without crossing into landing operations. Apollo 11 performed lunar orbit insertion behind the moon, settled into lunar orbit that became roughly 100 by 113 kilometers, about 62 by 70.5 miles, and then prepared to send Eagle down to the surface. Artemis 2 does not do that. NASA's current mission profile has Orion flying past the moon on a free return path, with a closest approach of roughly 4,000 to 6,000 miles above the surface, about 6,400 to 9,700 kilometers. That is close enough for the moon to dominate everything the crew sees and does, but it is still far above the surface and far outside landing operations. That is the dividing line. Apollo 11 crossed into the moon's working zone. Artemis 2 stays in the moon's test zone. That distance changes the meaning of the mission. Apollo 11 treated the moon as a workplace. Once the spacecraft got there, every important action was about using lunar orbit to support a landing. At 100 hours, 12 minutes into the mission, Eagle undocked from Columbia. Then it entered descent orbit, and then it went down toward the Sea of Tranquility. During powered descent, Neil Armstrong had to take partial manual control to avoid hazards and get the spacecraft to a safe landing site. The moon was not just the destination, it was the place where the hardest work happened. Artemis 2 uses the moon differently. Orion will use the flyby to validate navigation, observation procedures, crew operations and science support in a real deep space environment. So one mission physically engages the moon. The other uses the lunar environment to test the whole human and spacecraft system around it. And that sounds less dramatic only if you reduce the moon to one image: boots on the surface. In operational terms, Artemis 2 is doing something more basic first. NASA wants to know whether a crew can travel all the way out there, work effectively, manage the spacecraft, observe and document what they are seeing, handle communications limits, and come back safely before the program adds the even bigger risk of a landing mission. That means the moon is being used almost like a final exam environment. It gives Orion real distance, real delay, real geometry, real isolation, and real consequences. You cannot fake that in low Earth orbit. You cannot fully simulate it on the ground. Apollo 11 needed the moon as the place where the mission succeeded or failed. Artemis 2 needs the moon as the place where the transport system proves whether it deserves the next step. Then there is the part that links both missions in a very direct way: the far side blackout. Apollo 11's key lunar orbit insertion burns happened behind the moon and out of contact with Earth. That was one of the most tense parts of the mission, because mission control had to wait in silence while the spacecraft did exactly what it needed to do on the far side. Artemis 2 also disappears behind the moon. NASA says Orion's crew will lose communication with Earth for about 30 to 50 minutes during the farside pass, but the purpose is different. Apollo used that blackout to slip into lunar orbit and set up landing operations. Artemis 2 uses that blackout as part of the flyby itself, while the crew photographs the far side and makes scientific observations during the period when Earth cannot see them. Same balance, different mission logic. That is one of the strongest comparisons in the whole story, because it shows how the same physical reality can serve two completely different programs. The moon still blocks radio contact. The geometry still forces a period of isolation. That part did not change in 50 plus years. What changed is what the mission is doing with that silence. Apollo 11 used it for critical orbital operations directly tied to landing. Artemis 2 uses it as part of a planned observational and operational phase. The crew will be looking outward, documenting the far side, describing features, and working through a period of real separation from Earth as part of the mission design. So even when the two eras touch the exact same wall of physics, they are using it for different reasons. And NASA's own comparison image makes this hit harder because it is so simple. From Orion's closest flyby distance, NASA says the moon will look about the size of a basketball held at arm's length. That tells you two things at once. First, the moon will feel close. It will fill the view in a way that makes the mission emotionally and operationally lunar, not just space nearby. Second, it also tells you the crew is still not in the zone Apollo 11 entered. A basketball at arm's length is near enough to study and feel, but it is not under your feet. Apollo 11 crossed the line from seeing the moon to working on Summit. Artemis 2 deliberately stops short of that line because the mission is about proving the vehicle, the crew procedures, and the larger architecture before a later crew tries to cross it. That is why calling Artemis 2 a weaker moon mission does not really hold up. If you only measure success by landing, then yes, Apollo 11 did more at the moon. But that is not the right comparison. Artemis 2 is not there to beat Apollo 11 on drama. It is there to answer a harder program-level question. Can this system operate in lunar space in a disciplined, measurable, repeatable way? NASA is not trying to win a race with this mission. NASA is trying to remove unknowns from the missions that come next. So the moon stops being only a target and becomes a test environment. That can sound smaller until you realize it is what makes repeated missions possible. A one-time landing can survive on extraordinary effort. A lasting campaign cannot. There is also a psychological difference here that matters. Apollo 11 arrived at the moon with the mission's biggest commitment still ahead. The crew had to go from orbit to descent to touchdown, knowing there was no historical template for what they were about to do. Artemis 2 arrives knowing it is not supposed to force that final step yet. That changes how the crew uses the moon. They are not there to squeeze everything toward a landing sequence. They are there to gather operational confidence, how the spacecraft behaves, how navigation and observation work this far out, how the crew functions during a true lunar flyby, and how mission control and the crew handle the most real rehearsal humans have had in that environment in more than 50 years. In Apollo 11, the moon was the center of action. In Artemis 2, the moon is the place where the action reveals whether the system is mature enough for later landing missions. So the moon is doing two different jobs in these missions. For Apollo 11, it was the target in the most direct possible sense. Get there, orbit it, land on it, leave it, return home. For Artemis 2, it is the operational environment that exposes whether the transport system, the procedures, the crew and the support network are ready for the missions that will try to do more. That is not a downgrade, it is a shift in purpose. Apollo 11 proved humans could reach the moon and work there once. Artemis 2 is trying to prove humans can start building a way to come back again and again, without treating every mission like a one-time gamble. And that creates the next problem immediately. If Apollo used human manual control to save the most famous part of the mission, then what does Artemis 2 do with manual control when the mission is not trying to land at all? Then what is the role of the human pilot now? In Apollo 11, manual control became famous because it arrived at the exact worst moment. During the final descent, Neil Armstrong saw that Eagle was being taken toward rough terrain near West Crater, with large rocks and a bad landing area. He took partial manual control, flew past the hazard, and guided the lunar module to a safer spot. That moment stayed in history for a reason. It showed that the software, the sensors, and the planned descent path were not enough by themselves in every real condition. At the edge of success and failure, human beings still had to see the problem, make the decision, and fly the spacecraft. In Apollo 11, manual control was not a nice feature. It was the last layer between mission success and disaster. That is why people often talk about Apollo manual control in almost mythic terms. But if you stop there, you miss the more important comparison. Artemis 2 also puts manual control at the center of the mission, just in a very different way. NASA has built a manual mode proximity operations demonstration directly into the flight plan. After Orion separates from the upper stage in high Earth orbit, the crew will switch the spacecraft into manual mode and fly relative to that stage, using it as a stand-in target for future docking missions. NASA is very explicit about why this is in the mission. The agency says this test will provide performance data and operational experience that cannot be readily gained on the ground, and that it is preparation for critical rendezvous, proximity operations, docking, and undocking in lunar orbit beginning with later Artemis missions. That means manual flying is no longer just something you hope the crew can do if the day goes bad. It is a formal mission objective. And Artemis 2 does not stop there. NASA's Artemis 2 daily agenda also includes a later manual piloting detailed flight test objective during the return phase. The crew will steer Orion through a set of tasks, center a chosen target in Orion's windows, move into a tail-to-sun attitude, and compare different control modes while engineers gather more data on how the spacecraft handles in deep space. Oh, that is a major clue to how the program thinks now. Apollo 11 had manual intervention at the most dangerous point because reality forced it. Artemis 2 plans manual handling earlier and later because NASA wants to measure what humans and the spacecraft can do together across multiple conditions before those skills are needed near the moon on docking and landing support missions. So the easy line would be to say Apollo trusted astronauts more and Artemis trusts automation more. That is not actually true. Apollo already had the seeds of the modern idea. The Apollo 11 press kit states that after second stage ignition, the crew could manually steer the Saturn V if needed. That tells you NASA did not see astronauts as passengers even in 1969. The vehicle had backup paths where human control mattered. There were already procedures for what would happen if the inertial platform failed and the crew had to take over guidance and control functions for the launch vehicle. So the old program always kept a place for human authority. The difference is not that Apollo believed in pilots and Artemis does not. The difference is that Artemis turns human-machine interaction into a tested, measured data-producing part of the mission, instead of mostly treating it as a backup for when the mission is already in trouble. That changes the meaning of manual control completely. In Apollo 11, manual control proved that a trained astronaut could rescue a mission from edge cases the system had not fully handled. Armstrong's intervention showed that real terrain, real dust, real descent conditions, and real timing pressure could still push the machine outside its clean plan. In Artemis 2, NASA is not waiting for a crisis to reveal those limits. NASA is creating planned piloting tasks so the crew can intentionally expose the handling qualities of Orion, the workload involved, the response of the control system, and the usefulness of cockpit displays and procedures. It is a very different use of the human pilot. Apollo used manual control to save the mission in a frontier environment. Artemis uses manual control to map the performance envelope before future missions depend on it. And this is where the risk model changes in a very serious way. Apollo accepted that some unknowns would only reveal themselves in the middle of the mission. That was not because NASA was careless, it was because Apollo was pushing into a spaceflight frontier at incredible speed, with the landing itself as the final proof. If something unexpected happened, the crew might have to improvise under pressure. That is one reason Apollo astronauts became legends. They were trained to step in when the machine, the plan, or the environment stopped lining up cleanly. Artemis still values that human ability, but it does not want to discover the limits that way if it can avoid it. Artemis wants measured handling data, validated procedures, refined training, and known performance margins before the future mission depends on a crew improvising in lunar orbit or near a landing sequence. That is a huge program-level shift. Apollo accepted improvisation as part of frontier flight. Artemis is trying to reduce how much improvisation later missions will need. You can see that in how NASA talks about Orion piloting. The agency says the proximity operations demonstration is there to evaluate manual handling qualities and to get the spacecraft completely ready for later missions. Even Reed Wiseman described the point very directly. Most of the time Orion will fly autonomously, but having humans aboard gives the program a chance to help future mission success if something goes wrong. That is not a rejection of automation. It is a more disciplined version of trust in the crew. The system flies itself most of the time because that is efficient and consistent. But the humans are being integrated into the loop in a deliberate, measured way because future missions will need both machine stability and human judgment. And that matters a lot once you remember what Artemis is trying to become. Future missions will involve docking in lunar orbit, transfers between spacecraft, more complicated operations near the moon, and eventually support for sustained surface missions. If manual control is only treated as an emergency skill, then NASA learns about its real limits too late. Artemis 2 is designed to avoid that trap. It uses the upper stage as a target, practices approach and backing away, and later runs another detailed piloting test because the program wants real data on how astronauts interact with Orion when the spacecraft is moving, rotating, pointing, and being commanded in deep space. That is not less serious than Apollo's manual control story. It is serious in a different way. Apollo proved that humans could take over when the mission was already on the line. Artemis is trying to prove that humans can be part of a modern deep space control system before a crisis forces the lesson. So the real comparison is not Apollo had more human control or Artemis is more automated. Both ideas are too shallow. Apollo showed that highly trained astronauts could save a lunar mission when the system met reality at the worst possible moment. Artemis 2 is showing something different, but just as important. Astronauts can be built into a modern spacecraft's control loop as a planned operational element, with performance measured, procedures refined, and limits understood before those skills become mission-critical in lunar orbit. Apollo proved humans could rescue the future. Artemis is trying to prove humans and automation can prepare the future together. And once manual control stops being only an emergency story and becomes part of the system design, the next question gets more personal. If the crew is being tested this carefully, then what is life inside Orion actually like day after day? And how different is that from the way Apollo treated the astronauts' living space? Then you get to the part people usually underestimate. What it is actually like to live inside the spacecraft. Volume changes everything because volume changes how people think, move, sleep, work, and handle stress. NASA says Orion has a habitable volume of about 9.34 cubic meters or 330 cubic feet, which it compares to about 2 minivans. NASA also says that is nearly 60% more room than the Apollo Command Module, which had about 5.95 cubic meters or 210 cubic feet. That does not mean Orion is spacious. 4 astronauts in 330 cubic feet for a deep space mission is still a tight environment, but it is not the same level of compression Apollo treated as normal. Apollo put people into a very small control volume because the main goal was getting to a landing attempt as fast as possible. Artemis 2 is still confined, but now the cabin has to function as a working deep space environment for a larger crew carrying out a much wider set of tasks. That sounds like a small design difference until you think about what those extra cubic feet actually do. More room does not make the mission easy, but it changes the pace and the workload. NASA's Orion interior allows seats to be reconfigured after launch, so the crew can move around more once they are in space, and that matters because Artemis 2 is not treating the cabin as a place the astronauts simply endure while the real mission happens somewhere else. The cabin itself is part of the mission. NASA wants to see whether 4 people can function inside that volume through launch, checkouts, exercise, sleep, daily tasks, manual operations, and the trip to and from lunar distance. Apollo also had to keep its crew alive and productive, but the mission architecture pushed so much attention toward the landing sequence that habitability was treated much more as a tolerated constraint. Artemis 2 treats habitability as a system that has to be understood in detail before later crews go even farther. And that leads straight to the real point of this section. Artemis 2 is explicitly a life support shakedown. NASA says one of the early crew tasks, while still close to Earth, is to assess the performance of Orion's life support systems needed to generate breathable air. NASA also says the crew will evaluate how those systems handle carbon dioxide and water vapour produced when astronauts breathe, talk or exercise, and the long Earth orbit phase gives engineers a chance to see how the system behaves during high metabolic periods like workouts and low metabolic periods like sleep. That is a very different mission posture from Apollo 11. Apollo absolutely depended on life support working, but Apollo 11 was not structured as a mission whose identity centered on validating a new deep space crew habitat and transport system. On Artemis 2, life support is not just background machinery. It is one of the things the mission is there to test and characterize for later lunar flights. That is why ordinary daily life suddenly matters a lot more than it did in the old public image of moonflight. NASA describes Orion as having a potable water dispenser for rehydrating food and drinks, a compact briefcase-style food warmer, and a meal plan built around the astronauts' nutritional needs and individual preferences. NASA's public mission material explains that the Artemis 2 menu includes a large set of pre-selected foods and beverages because the spacecraft cannot be resupplied, and every routine has to work cleanly inside a small closed environment. That may sound mundane, but it tells you exactly what Artemis is trying to become. Deep space flight is no longer being treated as one dramatic push where daily life is just something the crew squeezes in around the important parts. Food, hydration, routines, and workload management are now part of mission architecture because they directly affect performance, morale, and how reliable the system will be on future flights. The same thing is true for exercise and other routine activities. NASA's daily agenda for Artemis 2 includes workouts early in the mission, and NASA explicitly says those workouts will provide another test of Orion's life support systems before leaving Earth orbit. That tells you how modern NASA thinks. Exercise is not just for keeping the astronauts healthy, it is also a way to push the environmental control system while the crew is still near Earth, and the mission team can study how the spacecraft handles changing metabolic demand. Apollo crews obviously worked and ate and slept too, but Artemis 2 is much more systematic about using those ordinary activities as measured operational inputs. The everyday life of the astronauts is not separate from the engineering test. It is part of the engineering test. Another detail makes that shift even clearer. After launch and early operations, Artemis 2 astronauts remove the Orion crew survival system suits and spend most of the in-space mission in plain clothes. NASA says they put the suits back on later to prepare for re-entry and ocean recovery. That detail matters because it shows what Orion is supposed to be during most of the mission. Not just a sealed vehicle for getting from one major event to another, but a cabin that is expected to work as a lived-in environment. The suits are there for launch, emergencies, high-risk phases, and re-entry. The cabin is expected to take over as the normal human environment in between. Apollo 11's major operational complexity revolved around the split between Columbia and Eagle, the landing sequence, the surface EVA, and all the transitions that came with that architecture. Artemis 2's complexity is different. It is more about keeping 4 astronauts functioning inside a deep space transport profile over time. And that does not mean Orion is comfortable in any casual sense. It is still a small capsule, privacy is limited, storage is limited, movement is limited, every object has to be managed, every routine has to fit around the spacecraft. Even basic systems like the toilet have been closely watched, because living in a spacecraft for days is not a side issue when there is no quick return option. But the point is not to sell Artemis as easy. The point is that NASA is treating crew habitability as something that has to be measured, refined and trusted if humans are going to keep going back beyond low Earth orbit. Apollo accepted extreme cramped conditions because the objective was to reach the moon first. Artemis accepts confinement too, but it is trying to understand confinement as a long-term operational variable, not just the price of a single historic attempt. That is the deeper change. Apollo treated crew habitability as the minimum tolerable cost of getting a lunar landing done under enormous pressure. Artemis treats crew habitability as one of the foundations of repeatable deep space flight. If a crew cannot reliably breathe, eat, sleep, work, exercise, remove the launch suits, use the spacecraft as a real living environment, and stay effective for the whole mission, then the transport system is not ready no matter how powerful the rocket is. That is why this section matters so much. The more ordinary Orion looks on the inside, the more radical the program change actually is. Artemis 2 is not trying to prove that humans can survive one extraordinary trip. It is trying to prove they can function inside a managed system that later missions can build on. And once you understand that, the next contrast gets even harder to ignore. Because the spacecraft interior tells you how Artemis wants people to live during the ride, but the suits tell you what Artemis thinks could still go wrong on that ride. Then the suits tell you something harsh about the mission that the rocket and the flight path only hint at. Apollo 11 dressed its astronauts to go outside and work on another world. Artemis 2 dresses its astronauts to survive the ride if the spacecraft itself gets into trouble. That is a very different problem, and once you see it, you stop thinking these missions are just two versions of the same moon trip. Apollo 11's suit problem was surface exploration. Neil Armstrong and Buzz Aldrin were not just wearing pressure garments for launch and landing. They had to step out onto the moon, move around, collect samples, deploy experiments, take photographs, and stay alive in vacuum while covered in dust and exposed to extreme conditions. NASA's Apollo 11 press kit describes the EVA setup very clearly. Both moonwalkers wore portable life support system backpacks with attached oxygen purge system units, and the full extravehicular mobility unit included the pressure garment, liquid cooling garment, portable life support system, oxygen purge system, visor assembly, communications, telemetry, and its own power supply. NASA also laid out the moonwalk plan around that suit system: contingency sample collection, documented sampling, experiment deployment, photography, and later bulk sample collection. In other words, the suit was not just clothing. It was a small life support vehicle wrapped around the astronaut so the astronaut could work on the moon. That is why Apollo's most famous suit looks different in meaning from Artemis 2's suit right away. Artemis 2 astronauts wear the orange Orion Crew Survival System suit, or OCSS. NASA describes it as a suit designed for a custom fit and equipped with safety technology and mobility features to protect astronauts on launch day in emergency situations, during high-risk parts of missions near the moon, and during the high-speed return to Earth. NASA also makes the distinction directly. Some suits are made to be self-contained personal spacecraft for use outside a vehicle during spacewalks, while another kind is worn inside a spacecraft during high-risk phases like launch and re-entry. That is what OCSS is. It is not a lunar surface suit. It is not a moonwalking suit. It is a pressure suit built to keep the crew alive inside Orion during the most dangerous parts of the mission and during spacecraft emergencies. And the number that changes the whole feeling of the mission is this one. NASA says astronauts could survive inside the OCSS suit for up to 6 days as they make their way back to Earth. That is a brutal detail because it tells you exactly what Artemis is planning for. This is a program that assumes deep space crews may have to survive after a total cabin pressure loss or air contamination event while they are still far from home. NASA's Orion Crew Systems documentation says Orion has an integrated crew survival capability using pressurized suits for several days in order to return the crew home safely if the cabin environment is lost. That is not surface exploration logic. That is failure tolerance logic. Apollo absolutely had redundancy and emergency planning, but the suit system people remember from Apollo 11 was optimized around EVA on the lunar surface. Artemis 2's suit is optimized around keeping humans alive inside a damaged transport vehicle long enough to get back. That also explains why NASA keeps improving things that sound small until you think about them in context. The OCSS helmet is lighter and stronger, comes in more than one size, reduces noise, and connects more easily to the communication system. The suit itself is custom fit for each crew member, rather than coming in broad off-the-shelf sizes. It includes a restraint layer to control shape and ease movement, and NASA says the zipper was re-engineered for quicker donning and greater strength. Even the boots were redesigned to fit better, help the astronaut move more nimbly, and provide protection in case of fire. Those are not random comfort upgrades. They tell you what the suit is supposed to do. Artemis 2 is preparing for launch loads, cabin emergencies, long wear time, communication needs, re-entry and survival in a spacecraft that has to remain credible as deep space transport hardware. Apollo's EVA suit had to let a person kneel, climb, sample, deploy equipment, and work in lunar gravity. OCSS has a different job description from the start, and recovery survival is built into the suit too, which makes the mission truth even clearer. NASA says each OCSS suit carries a life preserver and a survival kit in case the crew has to exit Orion after splashdown before recovery teams arrive. That survival gear includes a personal locator beacon, a rescue knife, and a signaling kit with a mirror, strobe light, flashlight, whistle, and light sticks. NASA also notes that the orange outer layer makes crew members easier to spot in the ocean if they ever have to leave Orion without immediate assistance. So this one suit is bridging launch risk, emergency spacecraft depressurization risk, high-speed return risk, and post-splashdown ocean survival risk in one system. That is a very different mission truth from Apollo 11's suit system, which had to bridge vacuum exposure, lunar dust, low-gravity movement, experiment work, and surface sample collection. Different suit, different mission reality. Ew. That is why the contrast hits so hard when you say it plainly. Apollo 11's suit asked a surface question. How do you turn a human being into a working explorer on another world for a few hours? The answer was a pressure garment plus backpack life support, purge oxygen, cooling, communications, and mobility built around EVA. Artemis 2's suit asks a transport question. How do you keep a crew alive if the cabin is compromised while they are still deep in space and still committed to coming home? The answer is a custom-fit survival suit that can ride through launch and re-entry, support the crew for days in a contingency, and carry recovery gear all the way to the ocean. The first question belongs to a landing mission. The second belongs to a system validation mission that knows credibility depends on surviving the worst case, not just the nominal one. And this is where the suit comparison stops being just a design detail and becomes a program-level statement. Apollo 11's suit was built around the idea that the crew had to leave the spacecraft and physically interact with the moon. Artemis 2's suit is built around the idea that the spacecraft itself is the thing being tested, so the suit must act like a final survival layer for the ride rather than a fieldwork system for the surface. That is why Artemis 2 can look less glamorous if you only compare iconic images. Apollo gives you the white suit on the lunar surface. Artemis 2 gives you the orange suit inside a spacecraft. But the orange suit is telling you something colder and in some ways more consequential. NASA is trying to make deep space transport believable under failure conditions before it risks a landing crew. If the crew cannot survive the ride, then the landing architecture above it means nothing. So the contrast that really matters is not old suit versus new suit. It is this. Apollo 11 dressed astronauts to walk on the moon. Artemis 2 dresses astronauts to survive the trip well enough that future moon missions can be trusted at all. One suit supported the first human fieldwork on another world. The other supports the hard engineering question underneath every future landing. Can the transport system fail gracefully enough and keep the crew alive long enough that the whole architecture deserves to continue? That is not the poetry people remember from Apollo. It is the cold filter every modern deep space program has to pass before it earns the right to make new footprints. And once the suit itself starts looking like an emergency shelter instead of a moonwalking machine, the next threat becomes impossible to ignore. Because now you have to ask, what kind of environment would make a deep space crew need that kind of protection in the first place? Then the mission stops feeling like a return to Apollo and starts feeling like something much more modern and much more exposed. NASA says Artemis 2 will be the first time in more than 50 years that humans go beyond Earth's protective magnetic shield, the magnetosphere. That one fact changes the whole temperature of the mission. The moon is not the only danger anymore, and in some ways it is not even the main danger in this part of the story. The real threat is the invisible environment between Earth and the moon. Once Orion leaves that magnetic protection, the crew is more exposed to deep space radiation, solar particles, and the kind of space weather that low Earth orbit missions do not face in the same way. That alone makes Artemis 2 fundamentally different from every human mission since Apollo. And Artemis 2 is not treating radiation as a vague background risk. It is treating radiation as something that has to be measured continuously, interpreted quickly, and folded into the mission as an operational variable. NASA says 6 radiation sensors inside Orion, part of the hybrid electronic radiation assessor system, will measure dose rates in different parts of the cabin. NASA also says each astronaut will wear a personal radiation tracker called a crew active dosimeter. That means the spacecraft is not just carrying people through deep space. It is watching what deep space is doing to the spacecraft and to the people inside it in near real time. Apollo 11 did not fly in an era with this kind of crew-centered onboard radiation awareness. Artemis 2 does. That is a major shift in how NASA thinks about human exploration. Then there is the German DLR sensor package, and this is one of those details that sounds technical until you realise why it matters. NASA says the updated DLRM-42EXT sensor flying on Artemis 2 offers 6 times more resolution than the Artemis 1 version for distinguishing between different particle energies. NASA's deep space research material explains that this matters especially for heavy ions, which are considered especially hazardous for radiation risk. In plain language, Artemis 2 is not just counting radiation, it is getting better at characterizing what kind of radiation the crew is actually dealing with. That is a much more advanced way to run a mission. Radiation is no longer something you mostly estimate after the fact. It becomes live mission data that can shape decisions while the crew is still out there. And this is where the mission profile gets even more revealing. NASA's Artemis 2 daily agenda includes a radiation shielding demonstration. The crew will assess how well they can protect themselves from a high radiation event like a solar flare by using Orion's own supplies and equipment to build a shelter if needed. That one planned activity destroys the idea that Artemis 2 is just Apollo with newer hardware. Apollo worried about getting to the moon, landing and coming back. Artemis 2 is also rehearsing how to survive the sun while on the way. That is a different kind of mission mindset. NASA is not just validating propulsion and navigation. It is validating survival procedures for a crew moving through a radiation environment that can change during the mission itself. That shelter drill matters because it tells you something very direct about the program's assumptions. NASA is not pretending the vehicle by itself solves every problem. The agency is building a procedure where the crew may have to rearrange the interior and use what is already on board to improve shielding in a bad event. That means radiation protection is being treated as layered defense. Forecasting, onboard sensors, crew dosimeters, alarms, procedures, and if needed, a temporary shelter configuration inside the cabin. This is much closer to how you would think about a Mars mission than how most people think about a classic moon mission. It is not enough to know the average environment. You need a way to react when the environment changes faster than the crew can get home, and Earth will still be involved the whole time. NOAA says forecasters will continuously monitor solar wind conditions during Artemis 2 and evaluate solar flares, coronal mass ejections, and solar energetic particle events that may occur. NOAA and NASA describe this as round-the-clock support. If conditions change, analysts can assess the threat and provide warnings to mission control and, if needed, the crew. NASA's own Artemis 2 radiation protection page makes the same point from the mission side. Orion's onboard systems can display warnings and sound alarms if radiation levels increase. So the modern mission is not just one spacecraft flying alone through deep space. It's a spacecraft embedded inside a life support network that includes heliophysics monitoring, radiation analysis, onboard sensors, and decision-making on the ground. That is a huge difference from the public image most people still carry from Apollo. That does not mean Apollo ignored radiation. It did not. Apollo had radiation concerns, and a mission planner's knew solar events could be dangerous. But Artemis 2 is operating in a much more instrumented and much more data-driven environment. NASA's modern radiation operations can combine onboard detectors, crew-worn dosimeters, Earth-based solar monitoring, and warning logic inside Orion itself. So the comparison is not that Apollo is careless and Artemis is careful. The comparison is that Artemis is turning radiation into something much closer to a managed mission input. It is measured at multiple points, tied to procedures, tied to forecasting, and tied to crew response. That is what makes the mission feel modern in a way that people often miss if they only look at the rocket and the moon. And this is where the bigger stake shows up. Apollo 11 proved that humans could reach the moon. Artemis 2 is trying to prove that humans can operate through deep space as living biological systems under continuous measurement. That is a much harder standard in some ways, because it means the mission is not only about mechanics, it is also about how the human body, the spacecraft, and the space environment interact in real time. Once you start measuring radiation that way, planning shielding drills that way, and running the mission with 24/7 space weather support, you're no longer just repeating a lunar mission from the past. You're rehearsing the kind of discipline needed for much longer missions, where the crew will be outside Earth's protection for far more than a few days. That is why this section points forward to Mars much more than most people realize. So the real line is simple. Apollo 11 proved humans could get to the moon and survive the trip. Artemis 2 is proving humans can move through deep space under active environmental surveillance, with radiation treated as something the mission has to track, interpret, and respond to while the crew is still out there. That is one of the biggest reasons Artemis 2 is not Apollo 11 again. It is not just going beyond Earth, it is learning how to stay operational when Earth's protection starts to fall away. And once that becomes part of the mission, the next question gets even sharper. If the environment itself is being studied this closely, then what kind of science is Artemis 2 really doing compared to Apollo 11? Then the science changes direction too, and this is where the mission stops looking like a repeat and starts looking like a setup for a much larger future. Apollo 11 did science by touching the moon. Artemis 2 does science by studying the crew, the spacecraft, and the environment while humans are moving through deep space. That is not a small difference. It changes what the mission is trying to learn, where the data comes from, and even what counts as scientific success. Apollo 11 asked what people could learn by standing on the moon. Artemis 2 asked what people must learn before standing there becomes normal. Apollo 11's science was physical contact science. Armstrong and Aldrin spent about 2.5 hours outside on the surface, and during that EVA they deployed the early Apollo scientific experiments package, which included a passive seismic experiment and a laser retroreflector, and that they also set up the solar wind composition experiment and collected lunar material to bring home. The Apollo 11 science report lays that out very directly. The crew's scientific tasks included placing a passive seismometer on the surface, deploying the optical corner reflector, exposing the solar wind composition experiment, and filling return containers with documented lunar material. This was science done with boots in the dust, tools in the hands, and instruments physically placed on the ground. And those instruments were not symbolic. The passive seismic experiment was the first seismometer placed on the moon, and NASA says it detected lunar quakes and provided the first detailed look at the moon's interior. The Apollo preliminary science report even notes that the instrument recorded seismic signals attributed to astronaut footfalls on the lunar surface. That detail matters because it captures the whole style of Apollo science in one image. The astronauts were not just passing through the environment. Their own movements were part of the measured interaction with the moon. That is tactile science in the most direct sense. The moon was the laboratory bench, and the astronauts were working on it in person. So what flips in Artemis 2? The first thing is the centre of gravity. NASA says the Artemis 2 crew will be both scientists and volunteer research subjects, and the mission includes 7 main research areas focused heavily on human health and system performance beyond low Earth orbit. One of those studies is ARCHER, Artemis Research for Crew Health and Readiness, which looks at sleep, stress, cognition, and teamwork. Another is immune biomarkers, which tracks how deep space may change the immune system using saliva and other samples. Another is AVATAR, which uses organ-on-a-chip devices to study how increased radiation and microgravity affect crew health. Artemis 2 standard measures adds a consistent set of health data, so future researchers can compare results across missions, and radiation studies inside Orion help connect the biological results to the actual environment the crew experienced. That is a very different scientific target. The science starts with the astronauts themselves. That means the crew is doing 2 jobs at the same time. They are flying the mission, and they are also generating the data NASA needs to build later missions. ARCHER will have participating astronauts wear wristband devices that track movement and sleep patterns through the mission, while pre-flight and post-flight tests look at cognition, behaviour, sleep quality, and teamwork. Immune biomarkers uses blood and saliva to study how deep space conditions may change stress responses, immune activity, and even dormant viruses. Standard Measures expands a broader astronaut health database with data gathered before, during, and after the mission. None of this is surface geology. None of it produces a rock you can hold in your hand. But it is exactly the kind of science a program needs if it wants humans to keep going farther than a single demonstration mission. And that is the inversion right there. Apollo 11 treated the moon as the primary scientific object. Artemis 2 treats the human in spacecraft system as a major scientific object too. NASA is not only asking what is out there, it is also asking what deep space does to sleep, stress, teamwork, immune function, radiation exposure, and operational performance when the crew is far from Earth and outside the usual protection envelope. That is why Artemis 2 feels less dramatic if you only watch for a flag or a sample bag. But from a program point of view, this is a major shift. Human exploration becomes something you study in detail, not just something you carry out and celebrate afterward. But does that mean Artemis 2 ignores lunar science? No, it just does it in a different way. NASA says that during the farside flyby, the crew will spend about 3 hours analysing and photographing geologic features such as impact craters and ancient lava flows. They will use geology training to describe shapes, textures, and colours in ways that help reveal the history of the terrain. NASA also says those skills will be critical to exploring the moon's south polar region on future missions. So Apollo 11 physically sampled the moon. Artemis 2 trains human beings to become better remote observers of the moon in a real operational setting. That is still lunar science, but it is science done from above rather than science done with boots on the ground. That distinction matters more than it sounds. A robotic orbiter can map the moon in great detail, and NASA has decades of orbital data already. But NASA points out that human eyes and brains are highly sensitive to subtle changes in colour, texture, and other surface characteristics. Artemis 2 gives scientists a chance to use human perception in a lunar flyby for the first time since the Apollo era, but in a mission whose main purpose is not landing. That makes the observation scientifically useful and operationally useful at the same time. The crew is learning how to describe what they see in language that later explorers near the South Pole can actually use. So even the lunar science has shifted from direct contact science to capability building science. Then the mission spread science outward, even more through the CubeSats. NASA says Artemis 2 will deploy international CubeSats from Germany, South Korea, Saudi Arabia, and Argentina in high Earth orbit, and each one has a distinct objective separate from the primary crewed mission. Germany's Tachilis will measure how the space environment affects electrical components used for future lunar vehicles. South Korea's K-RAD cube will use a dosimeter made of human-like tissue to measure radiation and biological effects across the Van Allen belts. Saudi Arabia's SHMS will measure space weather at different distances from Earth, including radiation, solar X-rays, solar energetic particles and magnetic fields. Argentina's Atenea will test radiation shielding approaches, measure Earth's radiation spectrum, collect GPS data, and validate a long-range communications link. So Apollo 11's science mostly rode in Armstrong and Aldrin's hands. Artemis 2's science also radiates outward through an international network of small spacecraft studying the environment around the main mission. That is another major clue that the program changed. Apollo 11's science was concentrated at one landing site and centered on what two astronauts could deploy and collect during one EVA. Artemis 2's science is distributed. Some of it happens in the crew's bodies, some of it happens in the cabin, some of it happens during lunar observations, some of it happens through separate international spacecraft riding along on the same launch opportunity. That is a very modern exploration pattern. The mission is no longer just one crew doing one set of experiments at one place. It is a layered scientific campaign with human research, systems research, lunar observation, and secondary payloads all running at once. So the cleanest way to say it is this. Apollo 11 asked, what can humans learn from standing on the moon? Artemis 2 asks, what must humans learn about themselves, their spacecraft, and the deep space environment before standing on the moon becomes repeatable? That one inversion explains almost everything. Apollo science was about contact, Artemis 2 science is about readiness. Apollo 11 brought home lunar material and left instruments on the surface. Artemis 2 brings home something different. Human data, system data, radiation data, observational data, and lessons that future crews will need before the program can treat lunar exploration as a sustained activity instead of a historic event. And once science itself turns from learn about the moon into learn how humans and the machines behave on the way to the moon, the next tension gets even sharper, because now you have to ask how a mission like this stays connected at all. The distance is old, the blackout is old, but the information system around the mission is not. So what changed if the moon is still the same distance away? The answer is that the distance stayed the same, but the information system around the mission changed completely. Apollo 11 already had an incredible communications network for its time. NASA's Apollo 11 press kit describes 85-foot antennas near Madrid, Goldstone and Canberra, placed about 120 degrees apart so at least one of them could see the moon at all times as Earth rotates. The same press kit says their data moved through NASCOM, a roughly 2 million mile web of landlines, undersea cables, radio circuits, and communication satellites back to Houston. That was a huge achievement in 1969. Apollo was not just a spacecraft flying to the moon, it was a spacecraft tied to a global nervous system built with the technology of its era. And that matters because people sometimes talk about Apollo as if it was only bravery and rocket power. It was not. It was also constant tracking, constant voice contact, constant telemetry, and constant handoff from station to station across the planet. NASA's own Apollo 11 press kit says that once the spacecraft got high enough, those big stations took over primary support, and the network was used not just for talking to the crew, but for tracking trajectory, planning burns, monitoring spacecraft systems, and setting up critical maneuvers all the way from Earth orbit to lunar orbit and back. So even in 1969, the moon mission was already a distributed control problem. The difference is that Apollo's network was mainly proving that Earth could stay connected to a moon mission at all. Artemis 2 starts from a different assumption. NASA says Artemis missions rely on both the near space network and the deep space network, with the two systems working together so Orion can be tracked and supported from launch through Earth orbit, around the moon and back home. NASA also says Artemis 2 will briefly go beyond the range of GPS satellites and NASA's tracking and data relay satellites, while still in Earth orbit, so the crew and mission controllers can do an early checkout of deep space network communications and navigation before heading farther out. That is a very different navigation stack from Apollo's era. It is not just inertial guidance plus ground tracking anymore. It is a layered handoff from near-Earth infrastructure to true deep space infrastructure, tested on purpose before the mission commits to the full outbound trip. And notice what that means. Apollo used Earth orbit mostly as the last setup before leaving. Artemis uses high Earth orbit as a place to verify the handoff between different communication and navigation systems. NASA's Artemis 2 press kit says the Near Space Network supports launch, Earth orbit, and the return to Earth, while the Deep Space Network takes over beyond low Earth orbit. NASA also notes that the Deep Space Network still uses the same 3 global locations people know from deep space history: Goldstone, Madrid, and Canberra, placed so one site can pick up the spacecraft as another loses line of sight. So there is continuity there, but the way those systems are integrated is much more layered now. Artemis 2 is not only trying to stay in contact, it is trying to prove that this handoff architecture works smoothly enough for future missions that will do even more near the Moon. Then there is the public side of communication, and this is where the two programs really separate. NASA says an estimated 650 million people watched Armstrong's first televised step onto the Moon. That tells you something basic about Apollo 11. Apollo did not just land on the Moon, it transmitted that victory to the whole world. The television signal was part of the event itself. Artemis 2 still has a public communications role, of course, but the deeper story is more operational now. NASA's Artemis 2 science material says scientists on Earth will provide real-time data analysis and guidance from a science evaluation room in Mission Control, while payload specialists in another control area monitor astronaut health studies and other science operations during the mission. Add in space weather forecasting, health monitoring, onboard radiation sensing, navigation support, and crew communications, and the network is doing much more than broadcasting history. It is actively managing the mission as it happens. That is why the communication system around Artemis feels less like a giant TV event and more like a live operating system. NASA's Artemis 2 science page says the crew will work with scientists on Earth during the mission, and the experts in impact cratering, volcanism, tectonism, and lunar ice will provide real-time analysis and guidance from Houston during the lunar science phase. The same NASA material says the payload operations team will manage astronaut health studies during the mission, and that NASA at NOAA will provide 24/7 real-time space weather forecasting and analysis. So the communication system is carrying much more than voice and telemetry. It is carrying science support, health support, environmental warnings, navigation, and operational decision-making at the same time. Apollo's network projected triumph. Artemis's network is built to support repeatable operations, but one thing did not change, and that is important. The Moon still blocks radio contact. Apollo 11 lost contact during key behind-the-Moon operations, including the first lunar orbit insertion maneuver. Artemis 2 also expects a blackout. NASA says Orion will lose communication with Earth for roughly 30 to 50 minutes when it flies behind the Moon, depending on launch date. So the basic geometry is the same. No software update, no new network design, and no modern mission planning can change the fact that the Moon itself gets in the way. That is a useful reminder that some parts of spaceflight are still controlled by the same hard physics Apollo dealt with. What changed is what the mission is doing around that blackout. Apollo used behind-the-Moon silence for critical orbital operations tied directly to a landing sequence. Artemis uses that same silence during a flyby phase when the crew will be taking photos and video of the far side and making observations to share with scientists once communication returns. So the blackout is no longer mainly the hidden doorway into a landing attempt. It becomes part of a broader operations and science sequence inside a mission designed to validate the whole transport and support system. The silence is the same. The job being done inside the silence is different. And this is where the comparison gets sharp. Apollo 11 proved that Earth could stay connected to a Moon mission using one of the most ambitious communication systems of its time. Artemis 2 is trying to prove something harder in a modern sense, that Earth can manage a moon mission as a distributed information system with navigation handoffs, deep space communication, real-time science support, astronaut health monitoring, and space weather protection all fused into one live architecture. That is a much more operational idea of exploration. The moon is still far away, the blackout is still real, but the mission is now wrapped inside an information network that is not just watching the crew go, it is helping the mission function minute by minute. And once the mission becomes that data-rich and that tightly supported, the next question gets even more brutal. Because if all of this information is flowing just to keep 4 people alive and effective for 10 days, then what happens when the spacecraft turns back toward Earth and has to survive the single most violent phase of the whole mission? Then the mission comes back to the oldest fear in deep space flight. Reentry looks familiar on paper, but it is still one of the most violent things human beings do. Apollo 11 came home from the moon at more than 25,000 miles per hour, about 40,000 kilometers per hour, and NASA's mission documentation made the danger very clear. At that speed, the spacecraft had to hit the atmosphere at the proper angle, or the return would go wrong. Too steep and the heating and loads could become catastrophic. Too shallow and the spacecraft could skip back out instead of coming home correctly. Artemis 2 inherits that exact same basic problem. The computers are better, the materials are better, and the systems are more modern, but the atmosphere does not care about any of that. A crew returning from lunar distance still has to meet Earth at enormous speed and survive a very narrow corridor between success and disaster. That is why re-entry is the place where all the big words suddenly stop mattering. You can talk about exploration, moon programs, architecture, and strategy for hours, but once the spacecraft turns heat shield forward and starts down, all of that gets reduced to one question. Does the machine actually survive the physics? Apollo 11 answered that question at the end of the first lunar landing mission. Artemis 2 has to answer it at the end of a qualification mission that is supposed to prove the return system is ready for later crews. Same furnace, different burden of proof. Apollo came home to close a historic achievement. Artemis 2 has to come home in a way that certifies a system others will trust. And Orion's heat shield is not a side detail in that story. It is one of the main characters. NASA says Orion's heat shield is 16.5 feet wide, about 5.03 meters in diameter. NASA also says that during return from the moon, Orion will be travelling about 25,000 miles per hour and face outside temperatures near 5,000 degrees Fahrenheit, about 2,760 degrees Celsius. NASA describes that as about half as hot as the surface of the Sun. That is the scale of the problem. Orion is not drifting back into Earth. It is slamming into the atmosphere so hard that the air itself becomes a lethal heating environment, and the heat shield has to absorb and carry away enough of that punishment to keep the astronauts alive inside. This is not just a protective layer. It is the difference between a controlled return and the wrong kind of history. And there is extra tension here because Orion's heat shield is not just a generic future promise. NASA publicly reviewed the Artemis 1 heat shield investigation in late 2024 after the uncrewed mission returned with more char loss than expected, and the agency said engineers would keep preparing the already installed Artemis 2 heat shield for the crewed flight. That matters because it reminds you this is not abstract engineering. Orion's thermal protection system has already been through real scrutiny. Artemis 2 is the mission where that system has to prove itself with people inside the capsule, not just hardware and test objectives. So when Orion turns home, it is not only re-entering Earth's atmosphere, it is also carrying the weight of lessons learned from the last mission and the pressure of proving that those lessons were enough. Then you get to the parachutes, and again the simple version is not enough. NASA says Orion uses a system of 11 parachutes deployed in precise sequence. After the atmosphere has already acted as a brake and cut Orion's speed from about 25,000 miles per hour down to roughly 325 miles per hour, those parachutes have to take over and slow the crew module to about 20 miles per hour, around 32 kilometers per hour, for splashdown into the Pacific. That is a huge change in speed handled in stages, and every one of those stages matters. The parachute system is not just there to make the ending look gentle, it is part of the return architecture that has to work in a repeatable way for future lunar crews. Apollo 11 also depended on a precise return and recovery chain, but with Artemis 2, NASA is not only asking whether Orion can survive. NASA is asking whether Orion can survive in a way that future missions can trust as standard practice rather than one successful exception. That changes how you should think about the whole descent. Apollo's return was already historic because it brought back the first humans who had landed on the moon. Artemis 2's return is historic for a different reason. It is a formal validation step inside a longer campaign. NASA's own Orion material says the spacecraft's parachute system is designed to ensure a safe landing for astronauts returning at high speeds, and NASA's Artemis 2 recovery preparations emphasize training with Navy support, helicopters and recovery teams because the splashdown is not just a finish line. It is part of proving the full return chain. If later missions are going to carry astronauts to lunar orbit, to docking operations and eventually toward landings, then the homecoming system has to look reliable, measurable and repeatable now. The timing makes the contrast even sharper. NASA says Apollo 11 initiated re-entry procedures 44 hours after leaving lunar orbit. The service module separated from the command module, the command module oriented heat shield forward, parachutes deployed at 195 hours, 13 minutes, and splashdown came after a total flight time of 195 hours, 18 minutes, 35 seconds. Artemis 2's return is also tightly sequenced, but NASA now presents it as part of a very explicit flight day script. For the current Artemis 2 mission timeline, NASA lists crew module and service module separation at 7:33 p.m, a crew module raise burn at 7:37 p.m, entry interface at 7:53 p.m, and splashdown in the Pacific at 8:07 p.m. on flight day 10. The structure tells you a lot. Apollo came home at the end of the first landing mission. Artemis comes home at the end of a test mission, whose return sequence itself is one of the things being validated. Same atmospheric physics, different mission meaning. And notice what that says about confidence. Apollo 11 returned from a mission that had already done the most famous part before the crew hit the atmosphere. The miracle had already happened. Re-entry was still dangerous, but emotionally it was the closing chapter of victory. Artemis 2 is different. The mission's whole purpose is to inspect, rehearse, and validate a lunar transport system, so the re-entry is not just the ending, it is part of the evidence. The heat shield, the control during entry, the parachute sequence, the splashdown, and the recovery operation all become data for what comes next. If any major part of that chain underperforms, NASA does not just lose a clean ending, it has to re-evaluate confidence in future crewed missions deeper into the Artemis campaign. That is why re-entry is where the comparison with Apollo gets stripped down to its most honest form. Both missions meet the same atmosphere. Both missions hit the same wall of speed and heating. Both depend on the same basic truth that a deep space spacecraft must come home through a very narrow path if the crew is going to live. But the emotional function of that return is different. Apollo 11's re-entry closed a miracle. Artemis 2's re-entry must certify a process. Apollo proved that one lunar mission could survive the furnace. Artemis has to prove that a modern spacecraft, under modern scrutiny, can take a crew through that furnace in a way later missions can build on. And then the meaning changes again the second the capsule hits the water, because Apollo 11 did not just return from deep space, it returned from the surface of another world. Artemis 2 comes home from lunar space, with a completely different kind of problem waiting after splashdown. Then the meaning of coming home changes too. Apollo 11 did not just return from deep space, it returned from the surface of another world, carrying lunar material nobody had ever handled before. That made recovery far more than a splashdown and a pickup. NASA's Apollo 11 records say the command module splashed down about 13 nautical miles from the USS Hornet, and within minutes the astronauts were being treated as possible biological contamination risks, not just returning heroes. Recovery swimmers passed biological isolation garments into the spacecraft. The astronauts put them on, came out of the capsule, were sprayed with disinfectant, and were flown by helicopter to the ship's mobile quarantine facility. NASA's mission log and Apollo 11 press kit both show the same logic very clearly. The crew, the command module, and the return material were all handled as if something unknown from the moon might pose a danger until proven otherwise. That sounds extreme now, but in 1969 it made sense. Nobody knew for certain whether lunar material might carry something biologically hazardous, however unlikely that seemed. NASA's Apollo 11 press kit says the Lunar Receiving Laboratory existed specifically to quarantine and test lunar samples, the spacecraft, and the flight crew for possible harmful organisms brought back from the lunar surface. The astronauts entered a 21-day quarantine counted from the time they lifted off from the moon. NASA's later historical summary adds that the command module Columbia and the lunar samples were also kept in quarantine, and that the samples totaled about 49 pounds, roughly 22 kilograms. So Apollo 11 recovery was not just about finding the capsule and getting the crew aboard ship. It was a full biological containment operation built on uncertainty about another world. That is what made Apollo 11 recovery one of the strangest and most complicated post-flight operations in space history. You had ocean recovery, helicopter transfer, shipboard handling, sealed quarantine facilities, transport to Houston, medical monitoring, sample isolation, and lab analysis all connected in one chain. NASA's records show the astronauts stayed inside the mobile quarantine facility until arrival at the Lunar Receiving Laboratory, where the quarantine continued. The mission report also notes that post-flight medical examinations continued during that quarantine period. So for Apollo 11, safe return did not end at splashdown. Safe return meant surviving the moon landing, surviving re-entry, surviving recovery, and also not carrying something dangerous back to Earth. That extra layer shaped everything that happened after the capsule hit the Pacific. Artemis 2 recovery is hard too, but for completely different reasons. NASA says a joint NASA and Department of Defense team will recover Orion and its 4 astronauts in the Pacific after the mission, using Navy divers, small boats, helicopters, and a naval ship. NASA's Artemis recovery material explains that teams will first stabilize Orion in the water, attach an inflatable collar, set up the front porch raft under the side hatch, and then help the astronauts exit safely before moving them to the ship. NASA also says the crew is expected to reach the ship's medical bay within about 2 hours of splashdown. That is a demanding operation, but now the central question is no longer, did they bring back alien microbes? The question is, can you recover a deep space crew and capsule cleanly, safely, and predictably enough that future lunar missions can trust the whole return chain? And NASA has been rehearsing that chain in detail. The agency says Artemis recovery procedures have been tested repeatedly in underway recovery tests in the Pacific using the crew module test article, a full-scale mock-up of Orion. NASA has also published images and reports showing Artemis 2 astronauts participating directly in those tests, including open water egress practice with Navy support. That matters because Artemis 2 is not just trying to survive recovery once, it is trying to validate the procedures, hardware, teams, and timing that later crewed lunar missions will rely on. Apollo's recovery had to work because the mission had already happened. Artemis recovery has to work in a way that becomes part of a repeatable campaign standard. And the absence of quarantine is one of the biggest clues that this is a different kind of return. Artemis 2 does not land on the moon. It does not pick up lunar dust. It does not bring back lunar samples. It returns from cislunar space, not from physical contact with the lunar surface. That means the whole post-flight posture changes. NASA's Artemis 2 recovery material talks about shipboard medical evaluations, transport back to shore, and return to Johnson Space Center. It does not describe biological isolation or sealed facilities for contamination control, because that is not the kind of mission this is. Apollo 11 ended under biological caution procedures. Artemis 2 ends under recovery discipline, medical monitoring, engineering review, and data assessment. That is a very different definition of what post-mission means. That difference changes the meaning of safe return. For Apollo 11, safe return meant bringing the crew home from the first lunar landing without letting the possibility of lunar contamination slip through the system. For Artemis 2, safe return means recovering 4 astronauts after a deep space validation mission, evaluating their condition, retrieving the spacecraft and its data, and feeding the results back into the larger Artemis campaign. NASA's Artemis 2 mission priorities document says one of the formal mission objectives is to validate post-splashdown recovery operations, retrieve flight hardware and data, and assess performance for future missions. That is a very clear statement of purpose. Apollo recovery closed the first landing mission. Artemis recovery opens the next phase of the program by turning the end of the flight into evidence for what comes next. And that is why the emotional contrast is so strong when you put the 2 missions side by side. Apollo 11 came back like explorers from a foreign shore whose dust itself might be dangerous. The astronauts were waved into quarantine, their spacecraft was quarantined, and the lunar rocks were quarantined because Earth had never dealt with material from the moon before. Artemis 2 comes back in a very different role. Its crew returns like operators from deep space. They are carrying no lunar rock, no surface samples, no contamination mystery. What they bring back is confidence data or warning data about Orion, recovery timing, crew health, procedures, communications, and everything else the next missions need in order to move forward responsibly. So this is the real contrast. Apollo 11 recovery was the end of an expedition to another world, and it had to be treated almost like the return from a biological unknown. Artemis 2 recovery is the end of a deep space systems test, and it has to be treated like a disciplined handoff from flight operations to campaign learning. Apollo came home carrying moon matter. Artemis comes home carrying mission evidence. Apollo's recovery closed a chapter that had already changed history. Artemis 2's recovery decides how much trust NASA can place in everything that comes after it. And once even recovery means something different, the final question becomes unavoidable. If Apollo 11 was built to win a race, and Artemis 2 is built to validate a system, then the biggest difference between them is no longer hardware or trajectory at all. It is the era each mission is trying to create. Then the biggest difference finally becomes obvious. Apollo 11 and Artemis 2 are not just 2 moon missions separated by time, they belong to 2 completely different ideas of what spaceflight is for. NASA states Apollo 11's primary objective in very plain words: perform a crewed lunar landing and return to Earth. That objective directly matched President Kennedy's national goal of reaching the moon before the end of the decade. Artemis sits inside a different framework. NASA says Artemis is about scientific discovery, economic benefits, exploring more of the moon, and building the foundation for the first crewed missions to Mars. NASA's Moon to Mars architecture documents go even further and talk about long-term utilization of the moon for science, discovery, and economic benefit, and about establishing an enduring presence. That is the real split. Apollo was driven by a deadline. Artemis is being built as exploration infrastructure. That sounds like a simple difference in wording until you see what it does to the whole mission logic. Apollo 11 had to prove one thing in the most public way possible. Humans could do the impossible once. Land on the moon, return alive, end the argument. Artemis 2 is part of proving something much harder in the long run. Humans can do difficult things beyond low Earth orbit repeatedly, with systems that can be checked, trusted, improved, and reused. That is why this mission is so full of validation work. Life support has to be characterized. Manual operations have to be tested. Radiation has to be monitored. International hardware has to perform as part of the core spacecraft. Recovery has to feed directly into later missions. None of that is decoration. It is what separates a historic event from a transportation layer that might actually support continued human operations beyond Earth. And this is where a lot of people underestimate Artemis 2 because they are still looking for the Apollo kind of payoff. Apollo 11 gave the world a single image that settled everything. Artemis 2 is aiming for something less cinematic and much more demanding. It has to help prove that future crews can rely on a chain of capabilities instead of on one perfect mission. If the life support works but the manual operations do not look solid, that matters. If the flight goes well but the radiation procedures reveal weaknesses, that matters. If the spacecraft returns safely but the recovery process shows problems, that matters too. Apollo needed one decisive success. Artemis needs a system that can survive scrutiny from every direction because the program is not trying to create one miracle. It is trying to remove reasons that later missions should not happen. Then there is the international side, and this is another place where the era shift is impossible to ignore. Apollo 11 was an American mission watched by the world. Artemis 2 is still American-led, but NASA's own partner material shows that the structure of the mission is international. The Orion service module is provided by ESA and built with contributions across Europe. The crew includes Jeremy Hansen from Canada. NASA's Artemis partner pages also show that international participation reaches into Gateway, service modules and other parts of the lunar campaign. The secondary science payloads on Artemis 2 also include CubeSats from Germany, South Korea, Saudi Arabia and Argentina. So the global audience is still there, but now parts of the spacecraft, the crew and the science system are global too. Apollo represented national achievement with worldwide visibility. Artemis is trying to build a coalition architecture that can keep operating after the headlines fade. That matters because it changes what success even looks like. In Apollo, success was easy to define. Did the United States land humans on the moon and bring them home first? Artemis' success is broader and in some ways less emotionally simple. NASA says Artemis missions will become increasingly difficult and are intended to build on one another. The agency's Moon to Mars objectives talk about communications architecture, navigation architecture, continuous human lunar presence, and a robust lunar economy. That means Artemis 2 is not just one mission trying to make history on its own. It is one mission inside a framework that expects later landings, later logistics, later science and later industrial capability around and on the moon. In Apollo, the mission was the event. In Artemis, the mission is also part of the platform for events that have not happened yet. The science target changes in the same way. Apollo 11's science centered on the moon itself. Lunar rocks, lunar dust, the surface, the seismometer, the laser retroreflector, and the solar wind experiment. Artemis 2 science is centered much more on the human vehicle environment system that has to work if lunar missions are going to become routine and eventually support Mars. NASA's Artemis science and crew research material makes that very clear. Artemis 2 includes health studies, radiation studies, sleep and performance tracking, cabin measurements, and lunar observations that are meant to prepare later crews. So if you only watch for footprints, Artemis 2 can look less dramatic. But if you watch for whether a spacefaring system is being built piece by piece, it becomes one of the most consequential crewed missions in decades. That is the part people often miss when they call Artemis Apollo again. Apollo was trying to prove that the barrier could be crossed. Artemis is trying to prove that crossing the barrier does not have to remain a once-in-history gamble. Apollo had to destroy disbelief. Artemis has to build reliability. Apollo had to answer, can humans reach another world? Artemis is trying to answer, can humans keep operating beyond Earth without treating every mission like a one-time stunt? Those are not the same challenge. The first one is about possibility. The second one is about durability. And durability is harder because it forces every part of the system to become real at the same time. The spacecraft, the life support system, the navigation, the crew training, the partner hardware, the recovery chain, and the science support. So this is the ending that matters. Apollo 11 told humanity that another world was reachable. Artemis 2 is asking whether human beings can build a reliable presence beyond Earth, without pretending every deep space mission has to be a singular miracle. Apollo shattered what people thought was possible in 1969. Artemis 2 is trying to challenge a different assumption now, that deep space is a place humans can only visit briefly, symbolically, and at enormous risk every single time. If Artemis works the way NASA hopes, then the moon stops being just a destination for rare heroic missions and starts becoming part of a larger operating zone for science, logistics, industry, and preparation for Mars. That is why Artemis 2 is not smaller than Apollo in any meaningful historical sense. Apollo 11 won a race. Artemis 2 is trying to help build an era. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.